Hi, Assalamualaikum. Today we continue with the part 2, chapter 9, in which we're going to do the quality tools and also the SPC, stands for Statistical Process Control. So for the quality control, it's the process of inspection and corrective action during production. So during this process, we need to do inspection so that we don't find any defect at the end of the process. And these are the tools usually applied, in which they have 7 QC tools for data collection and also for the interpretation, in which help in decision making. So we have the flow diagram, Checksheet, histogram, Pareto, we have the cause and effect diagram, scatter diagram, and control chart. So for the first one, flow chart, it's familiar, okay, in which the symbol represent meaning, in which they have operation, inspection, transportation, delay, and storage. So it shows the flow of the process. And we have Checksheet, in which it's an organized method for data recording. For example, this is to record the defect for each hour. So they are using the Checksheet. And histogram, distribution showing the frequency of occurrence of variables. So we have frequency, okay, for the y-axis, and then we have a repair time for the x-axis. So it shows here normal distribution. And also we have Pareto chart, in which is a method of organizing defect, problem, error, in which we can focus which one that we're going to look at. And usually we use the 80-20 Pareto rules, in which that usually the 80% of the output in a given situation is produced by the 20% of the input. So it means that it shows here on the complaints, we can see that the 20% of the problem, okay, is at this side, and the main one is actually coming from the top 2. Okay, so this is, we call it 80-20 rules. And usually we will tackle the first part here, in which they give us the highest complaint, in which on the overprice and small portion. So by having tackle these problems, so the rest of the 20 can also be solved. And the fifth one is the cause and effect diagram, also known as Ishikawa or fishbone. Okay, it's a structured brainstorming, in which it can explore what are the root causes. Usually for the fish head here, it's the effect, what happened. So for this case, they have bad burgers in the restaurant. So they look into, usually for the process, we look into the 4 main M's, in which we have manpower, method, machine, and materials. So machine, for example, the causes here is maybe due to the storage and cooking equipment. And then for the method, maybe the recipe, the materials, the ingredients involved. And then the person or the man here is maybe mishandling, okay, not enough training and so on. So here they add another 2 causes, in which measurement and also environment. And for services application, for example, if you have a complaint for the services, so you can add on equipment, policy, procedure, and people. So when you do the brainstorming and it's structured like this, so you know which one to go deeper. And the sixth one is a scatter diagram, in which to see the relationship between 2 measurements. Okay, we can see that whether they correlate with the 2 variables. Here we can see these are the strong positive correlation. This is not a strong one because it's scattered. This one you can see there's can form a straight line here, and this one, when you go this way, we call it the negative correlation. Okay, and the final one is a control chart, in which is related to time ordered plot of sample statistic. And this one we're going to look further, and we will do the calculation and the plot, in which most of the industry are using this to control their process. So they have the upper control limit, the lower control limit, and they have the process average or the central control limit. And usually they will check whether anything that go beyond the upper control limit or lower control limit. So we have two types of control chart in which we have the attributes and also the variables. And let's look at the control chart, in which the best tool for monitoring the performance of a process, in which by looking at the control chart, you can look whether the process is stable or not, and then you can predict whether the direction of the next process is going out of control or not, and then identify some of the causes of variation, and also special condition in which that monitoring needs to react instantly. Okay, they have to make decision based on the control chart. And when we talk about control chart, it relates with the SPC, in which we have variables, random variables, is mostly in which we have no control over it. For example, weather condition, in which abnormal, and another variable is the assignable variable, in which it can be identified, investigated, and can be solved. For example, if we have tool wear, okay, wear and tear, noise, vibration, or material defect, okay. And usually when we look in the quality for assurance, so we do sampling, okay. Accepted sampling is taking random samples of lot of batches. For example, if you are making pencils, so it's hard to do inspection each of the pencils, so we are going by taking some sampling for each batch. And usually by having inspection, the sampling, we can determine whether the whole batch have already passed the QA and QC requirements. So why do we do sampling? To know whether non-random sources variant exists, in which we can solve. For example, screws, okay, bottled water, in which you produce in a big lot size, so we use sampling. And sampling distribution, usually we have normal distribution. And in normal distribution, it helps to decide whether the process perform adequately or not. Okay, so if you have a very strict requirement, so you have a very clear, okay, on the inspection, so that what are the limits, okay, whether you want 99.74% or 95, so it depends on the requirement. And it depends on the control chart, in which when we combine, okay, when we look at these are the normal distribution, so it actually represents the upper control limit and the lower control limit. So we make sure that all the process measurement that we collected is within the upper control limit and lower control limit. And okay, these are the control chart. So we have two type control chart, in which the first one is the variable chart, and with the variable charts we will look into the X bar chart and R chart, and also the other one is the attribute chart. So we need to know that how to determine whether you want to have the variable charts or the attribute charts for the scenario. Okay, so attributes chart is more on the discrete numerical data, in which pass or fail, okay, in which we have P chart and C chart. So let's look at the variable chart first. So variable chart, in which the data of the process are measured and continuous, in which they have unit, for example, weight, kilogram, gram, length, in which you use centimeter, meter, or millimeter. And usually for a long item like this, or we have packaging with the weight, or we have the length of this pencil, so we can determine whether it passed or not the measurement that, so we have to take the measurement for each of the sampling. For the X bar, used to monitor the central tendency of a process, so in which that if they have the shifting upward of the peak here, so it will detect that there's a shift, and we need to see that this process is out of control. Okay, make sure that does not go exceed the UCL and LCL. And then these are the range chart. Okay, it's more on the size, okay, of the normal distribution. So these are the formula. Okay, for X bar chart, you need to find the formula for upper control limit and lower control limit. We gonna have X bar in which average of average, and then the Z value, okay, based on the confidence interval, and this is sigma, okay, the standard deviation of the sample means. These are for the range, okay, for the R chart, in which we have UCL and LCL. So for this, we are focusing on the X bar only, okay. So these are example of X bar chart. So the question is quality inspector took 5 sample. So they have 5 sample and each sample have 4. Okay, so n equal to 4. So every sample they take the 4 out of the batch. And they give you that they don't give you confidence interval, but they give you straight the Z value. And they also calculate already the standard deviation, in which 0.02 minutes. So if they give you a table like this, so the best is to make sure that the sample is going vertically, okay. So we need to convert this table into sample is vertically. So it's going to confuse if you do this way, okay. So you don't okay, what you have to do is you have to convert for easy reference, so that sample here is going vertically here, and then these are the number, the observation for each sample. So what you have to do, you have to take the each sample average, in which X bar. So we sum all these 4 and divide by 4. And then for sample 2, we have 4. Sample 3, we have 4. Sample 4 and sample 5. So this is very important because we need to find the sum of the X bar to get the X bar here. Okay. So for X bar, so we get the sum of X bar divided by 5 because we have 5 sample. So we have 12.11. So now we have Z from the question, and then we know that the observation is 1, 2, 3, 4, okay, per sample. Standard deviation given as 0.02. So we plug in for the UCL, we get 12.14, and for LCL we get 12.08. So we know that the upper control limit and the lower control limit, and the X bar is the central control limit. So now we can plot the graph. So what to plot here is the X bar. So X bar for sample 1 is 12.0, and then X bar for sample 2 is 12.12. Okay, 1, 2, so you go here, and then sample 3 is 12.11, sample 3 is 12.11 here, and so on. So you need to have 5 sample X bar. Then you do the central control limit first, in which CL is 12.11 from X bar, and then you have the UCL 12.14, and also LCL is 12.08. So what you can conclude from this process, you can say that there's none of the X bar is exceeding the UCL and LCL, so you can say that the process is in control. Okay, now let's look at attribute chart. So attribute means something that don't have a unit. For example, they either go pass or fail, operate or don't operate, and usually they have multiple sample of an observation. For example, tire, okay, you check whether it's good or not. The light bulb, whether it's can switch on or switch off, okay. And handphone also, you go for whether good or bad, okay. And C chart is another one, is for count number of defect, okay. For electronic, usually we use the P chart. So C chart is usually for defect, okay, defect and so on. So these are the formula. So for P chart, they have a longer formula in which you have to find the P bar, in which the total number of defect divided by the total number of observation, and then we have standard deviation. These are the formula, and we need to find the Z. So the UCL is P bar plus, and LCL is P bar minus, okay. And for C chart, they have very simple formula in which we have to find the mean or the average of defective, and also the UCL is just C bar plus Z times the square root of C bar, okay. For LCL is the minus. So let's see example. Okay, how to determine whether it's variable or attribute is look at the, is there any unit here? So there's no unit here. Okay, there's no kilogram, centimeter. So what type of chart is going to be variables or attributes? So we know that there's no unit here, no centimeter, gram. So it should be attributes. Okay, so fraction defective, no unit, no measurable, attributes, and what are they using? Using defect, in which fraction defective. So we know that it's not a C chart, but it's a P chart because they have fraction of defective. So the question asks that we have 10 sample and each sample they have 20 observations. So N, we know already what is N. And then control chart 95%. So we need to find Z value here from the normal table, and based on the plotted graph conclude the finding. So first of all, we already know that N is 20. N is the number of observation for each sample. 10 is the number of sample. Each sample have 20 units. So these are the table, and now we need to find the number of defect. So we know that it's 20. So 0.05 times 20, we get 1 defect. So we have to do for all 10 sample, and we need to sum to get the total number of defect because we're going to use in this formula. So total number of defective here is 18, and total number of observation is 20 for each sample. So total overall they inspected 20 times 10, so 200 tire they inspected. So we need to put the total number of observation, and we need to calculate. So 18 divided by 200, so we got 0.09. And for standard deviation, we have to use this formula. So P bar, we have 0.09, 1 minus P bar, again 0.09 here. And N, we know that each sample we have 20 observation. So square root, we have 0.06. Now, we need to find the 95% confidence interval. Find the Z from the normal table here. So remember in chapter 5, we did this. So 0.95 divided by 2. So find 0.475 in this normal table. So here. So what is the Z value? So we read here. So go horizontally 1.9 plus the vertical is 0.06. So we get Z value is. And now can we plug in into the UCL? Yes. So P bar we get 0.09. Z value is 1.96 and the standard deviation is 0.06, so 0.21. And for LCL, we plug in the numbers. This one become minus. And when we get negative, so we need to convert into 0 because there's no negative in the control chart. Okay. So now plot the graph. So these are information that we need, the UCL, LCL, and these are the CL. Okay, P bar is the control, is the central limit. So the first one is the CL, okay, 0.09 here. And UCL is 0.21 from here. And we know the LCL is on the 0. And what are these? These are the plot for the fraction defective. Sample 1 is 0.05 from here. Sample 2 is 0.15, 0.15 here. Sample 3 is 0.1, so 0.1 is here. So you have to plot all the 10 fraction defective for each sample. So what you can conclude from this, based on the plotted graph, conclude the finding, we find that none of this is exceed. So 0 is okay. So we can say that the process is in control. Okay. So you have looked into the variable, in which we look at the X bar chart, and in the attributes, we look at the P chart. So the next one is the process capability, in which we call it CPK, okay, CP. This is another way of determining and monitoring the process. Okay, these are the ability of a process to meet the design specification. And these are the formula. Okay, this is for the process capability ratio, CP, if the process is centered. And they have the 6 sigma. And for the process capability index, CPK, in which the process is not centered. So these are the formula. Okay. And process capability improving in which usually we have the target. And the step is simplify, standardize, mistake-proof, upgrade equipment, automate, and it will automatically improve the CP or CPK numbers. In which once we have improved the process capability, we need less inspection, we have lower warranty costs, in which less defect, fewer complaints, and also we have higher productivity. So for process control purpose, it means that narrower control limit is better because you will reduce the defect. So that's all for the SPC. Thank you.